and that's posted on Canvas. I was like, oh, I have some paper copies I'll hand out. I didn't bring them today. I can hand them out next time. I was like, if you want one, but I was like, you can print it and get it off of Canvas too. And that's just submit online or directly to me last day of class. Mostly the reason that this is take home is because it's really more just about the graphing software. And we're going to use something that you guys should all be familiar with. So what I really want to make sure that we focus on is identifying some shapes that you may and may not be familiar with, and then making sure you get them in the right form. And so this really dumps back to all the way to algebra. But these are some interesting topics that one last thing I want to make sure that we get through and you guys see. So starting with the basic concept, a conic, right? Word you should be familiar with derives from the word cone. Basically, if you have two cones, you line them up. If we take these two cones and we slice them various ways, we're going to get shapes in 2 dimensions that you should be massively, massively familiar with. And we're going to look at these 4, right? These 4, which you should be very, very familiar with. So if we slice it perfect, we get a circle. I've already talked about that a little bit. If we slice it slightly at an angle, right, we get an ellipse. And a circle is just a special case of an ellipse. So we're going to see the general form of what an ellipse is. Parabola, you should be ultimately familiar with. And then a hyperbola, all right? This one is basically just 2 parabolas, right, that line up, and they're mirror image of each other, and they have various special properties as well. So these are graphs, all right, that you actually should be familiar with. And since a lot of things in trig relate to triangles, and triangles then we always seem to come back around to circles, all right, these are just a few shapes that we should be familiar with. So let's start with the one that we are ultimately familiar with, the parabola. And so to refresh a couple of basic thoughts about a parabola, general form, y equals ax squared plus bx plus c. A is greater than 0, the parabola opens up. If it's negative, below 0, it opens down. All right, and notice that what's not on here, a equals 0, because if a equals 0, then what? Yeah, it's a line. It's no longer a parabola. You can find the vertex with the x coordinate value, or, all right, you can graph it. And the other thing we're going to do is we're going to look at putting this into vertex form, which we already did a little bit with as well. So because of what we're about to use, now I could use my calculator, but because we're about to graph a bunch of 3-dimensional shapes that violate the definition of a function, all right? Just want to refresh us on something that you likely have seen, Desmos. So Desmos, and literally I just Googled Desmos graphing calculator, all right? And actually it's in the notes later on as well. And so then I can write my equations into Desmos. Actually, this was 0.3. 0.3 x squared minus x plus 4. And Desmos is really nice in the sense that these little grayed out points, notice it highlights, right, your x-intercepts, your y-intercept, and the vertex. So the vertex there, all right, is negative 1.667, 4.83. And I mean, I can do that algebraically. X equals negative b all over 2a, where the b term is negative 1. and the A term is negative 0.3. And you will see, all right, that we end up, oh, that value must have been negative, hold on. Oh, negative 1.67. And we would see we get the same number out. Then you take that x coordinate, you plug it back in, right? You find g of negative 1.67. Plugging it in, and you would of course get 4.83. We can also do this on our graphing calculators, right? Besides using the graphing calculator for something like REF and quick tangent and things like that, there are so many better graphers out there that I just don't even bother using the graphing calculator, which is why Desmos just does such a good job. And especially as we start graphing other things, because the TI graphing calculators have one other big, massive restriction, all right, that's going to really, really mess us up. Okay, and so just for completion, okay, so it's about there, 1, 2, 3, 4, about there. And it looks something like that. The big things are, I mean, ideally we should know all about parabolas by now. It's open down, all right? And do we remember what that 0.3 does? Like that A value?
Stretching and compressing.
That is exactly correct. All right. And in this case, if the value is below 1, all right, it stretches it. If it is above 1, it compresses it. All right. And so those are the big concepts of basically graphing a parabola in standard form. What I want to talk about is the vertex form, because this is a much better form for us. All right, and we just saw this with our circles as well. Still, that A value represents open up, open down. But now instead of writing this in standard form, ax squared plus bx plus c, we write it in ax minus h quantity squared plus k. Because this is actually a better form for writing any standard function. And those standard functions include our trigonometric functions, right? All right, sine, cosine, tangent, all of those. This is graphing that we've actually done before. Because this value here means a shift which way?
Left or right?
And specifically, negative h means to the right. Okay, so remember it's always opposite sign of whatever that is. So this is a shift to the right in this case, but this is in general, shift left and right. And what does this k mean? Shifts up or down, and in this case specifically, because assuming k is positive constant at the moment, all right, we're shifting up, all right? Now again, if it's negative, you shift down. But this is just such a better form because when you have things in that form, all you have to do is identify the base function, and I can represent this graphically without even touching a calculator. All right, so I see, what's the vertex here of this equation f of x? What is it? One more time. It's not negative 3, 4. That's very close.
It's 3, 4.
It's 3, 4. All right, because again, opposite sign. All right, this one direct sign, so I know that like gets annoying, but I was like, it has to do with shifting left and shifting up and down. So the vertex is 3, 4. 1, 2, 3. 1. Okay, so the vertex is there. Is this open up or open down? How do you know it's open up?
There's no negative out.
The what is positive?
A is positive.
The A value, yes. A equals 2, all right, which is greater than 0. Open up. And then we just talked about it, and then it's slightly more compressed, but we don't really care about that like graphically. I just represent it as, okay, so it looks tighter. I was like, because that's basically the whole point, all right? We've got ourselves a parabola that's a little bit narrower, all right? And it's open up. And that's always what we want to do, all right? Watch the computers, calculators, whatever they are, they identify what this stuff is, right? We want to pick out the big information and then draw a sketch and then draw a better one, all right, in like with the technology. So to that end, let's practice completing the square yet again. All right, we should be just tip top at this, but it just never hurts to just keep practicing. So these are all techniques that we've done before because I have these parabolas in standard form, and this same concept is going to extend to our other graphs as well. And the big thing, all right, is keeping these values separate. Okay, so with completed square, what is first foremost that we need to pay attention to?
That front coefficient to one.
Yeah, that front coefficient is just killing us. Okay, now I've seen a lot of people like you can solve them, like bring them over to the left side and stuff, but a lot of times we want to do this without messing with anything. So it's not quite as easy as completing the square for our circles because you just like add it to both sides and divide and things like that. So this one, actually, we need to factor. And I'm just going to pull that 2 out of the x pieces. That 3, I'm going to leave at the end. So I'm just going to be focusing on this x squared minus 6. Once you have it in that form, then what do we do?
A, B, C thing?
Almost.
B?
B over 2, C. I mean, ABC, BC, B over 2C, right? But yes, all right, I like to identify these and I like to identify them explicitly just so we can keep track. So what is B in this case? -6. And yeah, make sure we keep that sign. And so then hence B over 2, which is -3. And then B over 2 squared is 9. So this one is slightly different. Okay, so now add and subtract the C value. Okay, and so I'm doing this because notice that because before we were, I mean, not quite solving, but because we had another side of the equation equal to a number, I was able to just add to both sides, and I still could do that, but I have to remember to bring stuff back, and it's kind of a hassle. And this 2 is what really messes with me. So notice that I'm adding and subtracting. So what number am I actually adding here? What do these 2 together make? 0. So did I change anything? No. Okay. Doing this helped me identify, and this is just one technique, and I think this is the best technique that sets you up for later, because the more complicated stuff we do, this, not in here, but in math in general. This concept of adding 0, multiplying by 1, 5 over 5, things like that. You want to make sure that you're not changing anything. It's why when we do common denominators, I emphasize so heavily. You don't, if it's 1/2 plus 1/3, oh, I don't multiply that one by 3 and multiply that one by 2. I multiply that one by 3 over 3, that one by 2 over 2, right? Because it's multiplying by 1. Okay, so we've got that. All right, and since I only need that piece, I'm going to pull that other piece out. So that's -9, but in order to get that out of the parentheses, what else do I have to do? The reason I added and subtracted it inside the parentheses is because there's that 2 associated, which means in order to get it out, that 2 has to come with it. So I'm not changing anything. And I'm just getting this into a prettier form. Okay, so what do we have back here? It says -18 plus 3, which is -15. And now I'm actually at the point where that is a perfect square trinomial, AKA something that can be factored, something I can write as x plus a number. And that number is
3.
almost
-3.
-3, right? It's always the b over 2 value. That gives me then 2 times x minus 3 quantity squared. And oh, look, I'm done. That's vertex form. So I want to graph these. Oh, we're just finding the vertex. So the vertex is, what is the vertex here, Charlene?
It's 3, -15.
Yep. And I have this in a nice, beautiful form, which I can do that with. Okay, what's the other one say? Okay, so I'm going to show the other method. And this method I hate a lot more. All right, but some people prefer this, and you may have seen this previously. Okay, so, and here's why, here's the other reason it's annoying. In order to do this and not confuse my g of x with x's, I'm going to switch that to that. We start the same. Okay. I need that a term to be what? Is it 1? No. It's -1, which is problematic. Okay, so that still presents us the same problem. But the concept with this method is this is a little more solvy. So I'm going to divide both sides by -1. So I divide both sides by -1. And then I need the x's alone. So I'm going to subtract 1 from both sides. Now, we still do a lot of similar things. It's just about how complicated those steps are in between. So once I get all the x's by themselves, then at the moment, I'm going to ignore the left side and I just look at the right side and I say, okay, once again, what's b? -10. And then hence b over 2 is -10 over 2, -5, -5 squared, which is 25. And now the difference on this one is add 25 to both sides. And we can still then identify what we're looking at. All right. So then my b over 2, which I lost, which is -5. So that is x minus 5 quantity squared. And once I'm here, then I proceed to bring everything back. And it doesn't seem too hard, minus 24 from both sides. Divide both sides by -1. And I could still identify the vertex just like we did before. And those methods feel really, really simple. Obviously, it's the same process. The reason I hate this one is it's this stuff at the end that I see everyone mess up. Because it's these literal last two steps. All right. All I had to do was subtract 24, and most people can get that part. It's whatever that A term was, people forget it way too much. So I'm dividing by -1, which means notice that went into both pieces. That negative became a positive 24. That positive x minus 5 squared became a negative. When this is a 2, a 5, a 1/2, all right, people forget their basic algebra skills, and it's that bringing back that I see all the problems, as well as actually I see the problems taking it away. So don't forget, we had to divide everything by -1 initially. I divided that whole piece, all right? All these signs flipped. So that's the issue, that there's so much going on that you forget one thing and it's all messed up. So, and here's the other thing. Something like our sphere that we were looking at and the shapes we're about to look at, right? This is a way that you may have learned it initially. I recommend you avoid this method because with things like spheres, hyperbolas, circles, ellipses, etc., we have more than just like a y on this side. We have an x, we have a y, we have a z. All right, we have way too many variables to bring things over to this side and back and forth, and this ends up taking much longer and is much more prone to mistakes. But I wanted to show both methods just so you can see those. Any questions there? We're all right? Relatively familiar, and we kind of knocked a little bit of the rust off of this already. Okay, the ellipse. The ellipse, actually, this form should be very, very familiar to us. This looks a lot like a circle, with the center, right, of the ellipse at these shifts. So notice the form now, okay? X minus h, y minus k. And again, these are just any constants, so you don't have to worry, oh my gosh, it's h or... This is the general form, and that's what I always want us to put our problems into. And it's because each of these pieces represents something. This is the shift on x, right? That would be in the positive direction of x, right? When that sign is negative. And this k value is the shift on y in the positive direction. Hence, the center of the ellipse, all right, is the value hk. Then those values a and b, those represent the distance. All right, now an ellipse, in case you recall, right? An ellipse is like an oval, okay? Or in case you do not recall, right? The value a and b, that's the distance, the x distance from the radius to the edge, and the value b is the distance of the y distance from the radius to the edge on the y. Now again, you're gonna have I graph these with technology as well, but you should be able to, we can identify and kind of adjust our equations to get them into what we call standard form of these conics. All right, oh, and so there's my link, desmos.com/calculator. All right, so our ellipse is So mostly what I want us to be able to do is we recognize the standard form. So I see this is an ellipse. Right? We know it has the standard form. We want to identify a couple of things, the center. And what is the center in this case? It's going to be just like one more time, Missy.
2, -4.
Almost.
Oh, 4, because they're squared, so 4 and 16, -16.
Just opposite sides. -2, 4. Yeah, I was like, and this extends from our parabola basic form. So it's -2, 4. All right, so that's our center. 1, 2, 1, 2, 3, 4. Okay, then let's get this into standard form. Now it's almost there. All right, so we're starting with an easy one, right? Now, ideally, right, according to the logic we just said, that means we should go 3 points off of the x-axis, and that should be the edge. 1, 2, 3, and 3 the other way. 1, 2, 3. And similarly, 5 off of the y. 5, 5. And that actually, those are our, I mean, as corner point as you can get on a circular object. All right. Those are the corner points of my object. So I should be able to basically sketch my ellipse, which I have totally ruined. And it should look something like that. Let's just verify this is what Desmos is for. So I put in those coordinates. All right, let's see if we can identify our center. 1, 2, 1, 2, 3, 4. Now notice, does it say where the center is? No. Okay, so Desmos is nice, but I mean, ideally you could kind of figure out where the center is. Also, all right, let's just double check. Okay, so wait, where was that? 2, 1, 2, 3, 4. All right, 1, 2, 3. 1, 2, 3. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. All right. So, and actually it does have the low point identified and the high point. It's got your X and Y axes. Notice it doesn't identify them over here. All right. So you kind of want to understand like the standard form and what's happening just to match it up with the picture. And I mean, so Desmos is really nice. Now, the reason I'm using Desmos here and I'm not using the TI calculator. On the TI calculator, in order to be able to graph something, it has to be a function. What is the definition of a function? Right? And maybe not the definition. There's a particular test it has to pass. Do we remember what that test is? You're the freshest in algebra. The vertical line test. Okay? You run a vertical line through your graph, and if it hits more than 1 point, that is not a function. This is technically not a function. Is this clearly a shape? Yeah. Okay? Just because something is not a function, so it lacks some of those properties. Does a circle have a lot of nice properties, or circle-related figures? Do they have lots of nice properties? Yeah. I was like, we're in trig. That's what we're doing. So even though this is not technically a function, this is a highly used shape, all right, that occurs in nature, right? That is basically the concept of why we talk about circles and ellipses, all right? They are things that were observed in nature, right? And then we identified formulas in order to give them mathematical meaning as well. All right, let's look at a couple more of these. Okay, Jada,
Sorry.
Don't mind if you sleep, don't snore. All right, so similarly, let's do another. X plus 5 squared. That's 4. Okay, now the big part of the general form of an ellipse, notice, all right, what it is equal to on the right side. It is equal to 1. So that is a big piece that we need to fix in order to get it into, right, standard form is always what we're going to look for. We want to write all these shapes in standard form. That way it is uber clear every piece of information that is identified. So along those lines, now again, I see this and it's something in the nature, what I want us to recognize, this is circle or ellipse related. Always want to try and start with the ellipse, since a circle is just a special case of an ellipse. So that means the easiest thing to do is I need to get this equal to 1. And again, so this is clearly an ellipse. We got this into perfect standard form with center where?
-4.
That is exactly correct. And then again, I could use Desmos, but I can sketch this pretty quick too. I was like, okay, so forward in both directions on X. 1, 2 points on Y. And again, an ellipse, same concept, but now this is shifted more in the X direction than it is in the Y direction. Are we okay? All right. The biggest part, all right, with all these conics is getting them into the correct form. All right, now I know I'm in the ellipse section here, but if I didn't know, do you know what shape this is? Can you identify what shape this is from right here? No, I was like, no one can. All right, so no matter what conic we're doing, all right, we need to complete the square. That's basically a part of life, all right, when dealing with conics. And we always want to get to that stage. So let's organize our X's, organize our Y's. And I don't need that 11, so I'm going to send that to the other side. And then this is the piece. Since I have X's and Y's and values in front of them, all right, this is where the factoring comes into play. So I'm gonna factor a 9 here. For the y's, I'm gonna factor a 4. Whatever that term in front of A is, and then we just complete the square individually, all right, on our two functions. Oh, whoops. Made that a lot harder. Factor the 9, that pulls 9 out of there. All right, so on this one, B equals -2. And then -2/2. And this is the whole part. Add and subtract that number. All I'm doing on those pieces is adding zeros. So, all right, with these guys, and then you can jump. I was like, I'm jumping some steps here, all right? Because basically, once I have this, I always know that it's just that piece. I know that it's that one. I know it's that one. All right, I can pull that 9 times -1 out and that 4 times -4 out. All right. I was like, so I know I can pull those pieces apart very quickly. All right, so this is x plus what?
-1.
-1. Y plus what? And we're pretty much almost in our form. I mean, that is the tough part of it. Okay, so let's see, I need to kind of bring those over. So that's -9, so that's 11 plus 9. And then that's -16, so that becomes plus 16. Oh, and that's already super good news. Because I know I have a number I like already. These values are just dead weight, and I need to get them to the other side because now it's really starting to look like a conic. And then the other big step for conics, divide both sides by that value. Okay, so let's see, what do we got? 9/30, 1/4. And that one's 9. And we are almost there. So this is an ellipse. All right. standard form, we definitely got that now. With what is our center at?
1, -2.
And it is super easy to identify, right? Once you get into the standard form, I actually see the shape, all right? I see what I'm looking at. I have an ellipse there. Okay, 1, -2. 1, -2. And again, we have Desmos, but these ones are just so fast. This is 2 off of that in the X directions, 3 off of that in the Y directions. All right, 2 in the X, 1, 2, 1, 2, 3 in the Y, 2, 3, 2, 3. And we've got our shape. Standard form, the whole point of it is that it represents something we're really, really familiar with. So the circle, which we are much, much more familiar with, right? A circle is just a special case in an ellipse when A equals B, right? So I have my equation for my ellipse. If I set A equal to B, so call them both A's, and then I multiply the whole thing by A, oh look, this is our equation of a circle or sphere that we were doing with all the vector stuff. And where A is our radius. So that's all a circle actually is. Special case of an ellipse. So with our circle, right, I have this in the form, and I can sketch the graph of my circle, identifying again the center and the radius. Now I could turn this into the form of an ellipse, but circle is one that, I mean, even before I think we talked about it, ideally you should have, I guarantee you saw it briefly at some point. All right. Okay, so this is a circle. Center at with radius equal 2. All right, so what is my center at?
3, -1.
3, -1. What's the radius?
Is it 3?
It's 3, because it's just square root of the 9. So circles are even easier. So, right, with ellipses, I was counting in both directions because I have that value. But technically, if I put that in the form of an ellipse, it would still say the same thing. It would say 3 squared in my denominators, which means I go 3 out on the X, 3 out on the X, 3 up in the Y, 3 up in the Y. So we change the form, but you can always write a circle in the form of an ellipse, all right? They both have kind of, quote, standard forms. And so 1, 2, 3, -1, and 1, 2, 3, 1, 2, 3, 3. 3. And so then we have a circle. All right, and our last shape, all right, one that you're probably less familiar with. You may have seen pieces of this, but again, since this is not a function, this clearly fails the vertical line test. Hyperbola, which was that slash where we get both pieces of a conic, right? Notice both these are conics, right? And it can be in either, all right, the X direction or the Y direction. It doesn't matter, all right? Same concept, all right, with the shape. And so they kind of look like parabolas, all right? Either 2 sideways parabolas or a parabola open up and open down. What's interesting about these is that, so these dashed blue lines that I have written here, those are asymptotes, all right? Specifically, they're slant asymptotes. All right, an asymptote, if you recall, is something that gets very, very close, but then never touches it. So these parabolas are actually restricted on those sides of the asymptotes. So standard form, actually looks very, very familiar to an ellipse, which we just saw when an ellipse is a circle. So all of these are very, very similar. Can you look at these two standard forms? What's the singular difference between these and an ellipse, actually, I mean?
The negative between them.
Yeah, it's the negative between them. All right, instead of plus, it's a minus. And that's really the only difference. Now notice that this one starts with an x minus the y's. This one is y's minus x. And that just determines, all right? So when it's x minus y, they open left, right. When it's y minus x, they open up, down. All right, that is basically the only difference of identifying. In both cases, the b value divided by the a value, all right, y equals plus or minus the b value, that gives us the slopes of the asymptotes, all right? And then then you do point slope form. I mean, that's all this last one is, the equations of the asymptotes. So they just give us something else to kind of find. These are kind of like, I can find a couple of things once we get into standard form, but with hyperbolas, they're the definition of I use Desmos, all right, in order to make sure. I can identify the pieces and I'm like, oh, okay, so it looks like this, and I kind of got the asymptotes. But I mean, as far as like getting good values for the points, it's kind of a pain. Also, I could find the center of the graph, right? But notice with the vertices, right? It's actually h plus or minus like the value, k plus or minus the value. So because they're offset, right? You don't know an exact like center. So you can find the center of where the graph is, and then you know it's like that. Okay. So this is almost already in standard form. Again, I'm gonna start with the base one here. And I mean, we can identify overall the exact middle. Center. Right, not the vertices or anything actually, but I know the exact middle of the graph is the 0.3, -1, just like we've been doing before. So I know that's the exact center, all right? Since this one is x minus y, all right? X minus y, that means I know it opens left and right. Then we can identify the asymptotes, which is usually, okay, so identify the vertices, and I mean, I use Desmos for that, all right? The asymptotes is the other interesting thing because Desmos doesn't actually draw these. So since we have our value, actually, okay, let's write this. So this is generic point slope form of a line, slightly different than what's written above, but same exact concept. And I wrote it like that because the y minus k value, that is that piece once you have it in standard form. So this becomes y plus 1. equals, okay, the only thing we have to identify is the B over A value, but that's always, all right, the Y value over the X value, right? Rise over the run. B, Y, A, X, all right? It always corresponds to that because that's, right, rise over run, slope of a line, all right? That is exactly consistent with what you already know. I lost it, 705. And then the X minus K value, so that's X minus 3. Now, the big part here is that this actually ends up, all right, with two different slopes, right? We have two different equations. Trying to think if I care enough to go further than that. I was like, I don't really. I could rainbow that through and find the equations. I was like, but the point is that these, all right, are the asymptotes. All right, we have two lines, all right, with slope positive 7/5 and negative 7/5 plus and minus a value, all right, which we wouldn't be able to see perfectly anyway. All right, let's graph this in Desmos just so we can see this guy. Mess with this one a little bit. X minus 3. That was. Okay, and I already forgot. What did we say? What was the middle point? 3, -1. 1, 2. X minus 3. Oh, my scale's all messed up. I'm like, wait a second. I was like, oh my God. I was like, it's not even close to 3, -1, because this is 10. Yeah, okay. 3, -1 is right here-ish. Because that's on 10s already. So, yeah, 3, -1, somewhere down right here, whatever the scale is, looks like my 2s. So yeah, which is like there, which is exactly where it should be. All right, identifying the center of the graph. And I mean, I could kind of see, okay, the scale's all messed up now because I just scroll out. But on a better picture, I could see, all right, that my slope is 7/5, which is also why we like to identify the asymptotes. All right, so we want to identify the asymptotes, all right? We want to identify that we're looking at a hyperbola, all right? And we want to get it in a standard form. That's always going to be our big goal. All right? I was like, and those are the 4 conics. When it comes to hyperbolas, I definitely let the computer do the calculating for me. Let's look at a couple more just for completion. And this one actually is in standard form, even though it doesn't look like it. So, all right, this one is 0, all right, for the y value, and the x value is -2, all right, comma 0. And just watch out that, notice that the x and y are written backwards, all right, so just make sure that it's still x comma y, all right, just because it's written backwards. And then my asymptotes, all right, so it's y equals, because it's y minus 0, so that one's actually done, plus or minus b over a, all right, where the y value, so 3 all over 1, x plus 2. Actually, this one actually is not bad. Y equals plus or minus 3x plus 2. And so again, it's always just the y piece, all right? Rise over the run, all right? Whatever the y value is. I know I'm saying b over a because that's what the formula says, all right? But I'm just always doing whatever value is associated with the y divided by whatever value is associated with the x, all right, in the denominator, right? 3 over 1. And especially with hyperbolas, all right, that you can see like the x's and y's are flipping. So make sure you're looking which one's x, which one's y. Otherwise, I was like, identifying the information, pretty simple. Let's just double check that graph. And I think that was reversed, right? That was y minus, so this one should be up and down. That was just 1, that was 9. Y squared over 9 minus x squared plus 2 squared equals 1. Okay. All right, and what did we say the center was? -2, 0. Ah, that one looks dead on. All right, -2, 0. All right, with some slopes that look pretty wide. I already forgot what were those? 3? 3. So with the slope of 3, I was like, let's see. My scale on the y's all messed up. I was like, that's the point. We trust the algebra, and you can verify that with a graph. All right. Not too bad. And then the part that actually adds a little challenge, gives us something to do, all right? The completing the square to get it into proper form. And again, at this stage, all right, I don't really know what I'm looking at. Okay. I can guess this is a hyperbola for one particular reason. Why? Anyone know? Because that's a negative, right? And that one's a positive. Because these are opposite signs, one minus the other. right? If they were both negative, actually, that means it's most likely it's an ellipse. So that is the singular guess that I think this is a hyperbola. I have no idea any other information about it, but just as an FYI. So you can identify these kind of from the get-go. So factor the A term. Then start your process identifying B over 2, and C in both cases. Now, also as a note, these are two crazy easy perfect squares. So I identified B over 2, and C just for always completion. But I was like, these ones, like after time, right, you can look at these ones and know what you're looking at. I know when I look at x squared plus 2x, I know exactly what I need to make that a perfect square. Same thing for that one. But the process never hurts to go all the way through just to make sure that you stay on top of it. Okay, let's see. So negative. Oh, oops. And then my B over 2, so that is x plus 1. And that one is -2. Okay, so let's see. -11 plus 16 is gives us 4, which is again a nice, beautiful number. And then while we're at it, I was just writing it in our standard form, and I flipped y and x just because the negative looks prettier behind, although it means the same thing. So I clearly see, so this is standard form. Is everyone okay with the algebra, right? I mean, I was like, I wasn't really narrating because it's like our 5th one of these we're doing, so this is a hyperbola with center at -1, 2. And asymptotes y -2 equals ±1 all over 2 times x plus 1. And be aware, it is perfectly fine to leave them in that form. I was like, this is the proper equation of a line. If you want to go the next step, you know, because you have to do this with a positive 1/2 multiplied through and a negative 1/2 multiplied through. But this is the proper form because you know, as long as you know there are two asymptotes, and this is the only case with asymptotes, so you should know that. And then just to verify, okay, so again, we got our center at -1, 2. Let's verify our graph. And here's the other nice thing. Again, Desmos will check me from the beginning. Okay, so we started with. Okay, and I already forgot, what was our center?
-1, 2.
-1, 2. Okay, so -1, 2. All right, there. Does that look like the center? Huh. All right, and again, I can put in my initial function, right? And Desmos verifies, oh, this is a hyperbola. And actually, I could put in my initial function and I could put in my algebraically rewritten function, make sure that they draw on top of each other. All right, so also another way to check yourself. All right. It's pretty good stuff. All right. I think that's a high note to end on.